In this episode, we will talk about LoRA code, LoRA adapters for code embeddings, semantic code search. It's super important, right? It lets us find code based on what it does, not just the exact words used.
Exactly. It's about meaning. But that's also where the challenge lies. Code is precise.
Yeah, the syntax, the context,
Yeah.
it all matters so much. And it changes between different programming languages. It's not like searching plain text.
Not at all. Traditional semantic search, the kind used for articles or web pages, it struggles with code. A keyword can mean totally different things depending on the language or even where it sits in the program.
And a little snippet of code doesn't make sense by itself, does it? You need the bigger picture.
Precisely. You need the surrounding program context. So developers trying to find useful code examples face this difficult choice. You've got tools that give a broad understanding, but maybe it's a bit shallow. Or you have these really powerful systems, but they're often proprietary, expensive, maybe a bit opaque.
Right. And we've seen open source models like CodeBERT that's bidirectional encoder representations from transformers and Unix coder. They've made progress for sure.
They have, but they often hit limits when you try to scale them up or you look at their efficiency for huge code bases.
And then the flip side, those high-performance proprietary systems, they work great, but the computational cost is just massive.
Astronomical sometimes. So it feels like you're stuck choosing between something accessible but maybe less powerful or something really effective that's just too costly or complex for many teams.
Exactly. Models like Voyage Code 2 or the OpenAI embeddings, they're impressive, no doubt.
Very impressive. But they tend to be closed systems. You don't always know exactly how they work under the hood.
And they might be designed more as general large language models that happen to understand code, rather than being laser focused on code retrieval specifically, right?
That's a key distinction. Plus, trying to fine-tune them to search effectively across, say, 6 different programming languages, that brings its own set of resource and scalability headaches.
Which is exactly where LoRA code comes in. It's trying to bridge that gap you mentioned.
Yes, trying to give us both the effectiveness and the accessibility.
So the researchers behind LoRA code are using this technique called low-rank adaptation. LoRA for short. It's a type of parameter-efficient fine-tuning, or PEFT. Okay, let's unpack that a bit. What does parameter-efficient actually mean here?
It means instead of retraining the entire huge model, which has, billions of parameters.
Right, which takes ages and tons of computing power.
Exactly. Instead, LoRA lets you create these much smaller, task-specific add-ons. They call them adapters. You only train these small adapters.
Adapters, like little specialized modules you plug into the main model.
That's a great way to think about it. And the low rank part refers to the mathematical structure of these adapters, which allows them to capture the necessary changes using far, far fewer parameters.
And just how few are we talking about?
It's actually quite staggering. LoRA code manages to fine-tune effectively using less than 2% of the base model's parameters. Think about that.
Wow, less than 2%.
Yeah. It dramatically cuts down on the computational resources needed, the memory, everything. It's like needing to adjust just a couple of small dials on a massive, complex machine to get it perfectly turned for one specific job.
And that efficiency translates to speed too, right?
Oh, absolutely. They reported training these adapters on 2 million code samples
8 million.
in just 25 minutes. Using 2 H100 GPUs, which are powerful, yes, but still 25 minutes for that scale is incredibly fast.
That really is remarkable. And the results, did this efficiency compromise performance?
Not at all. In fact, they saw significant improvements. For code-to-code search, that's finding code similar to other code, they saw MRR, mean reciprocal rank, increase by up to 9.1%.
Okay, 9.1%, that's solid.
But for text-to-code search using natural language to find code, the jump was even more dramatic, up to 86.69% increase in MRR.
86%, that's huge.
It is, and that's across multiple programming languages. Mean reciprocal rank, just to clarify for listeners, is a really common metric in search. It basically measures how high up the list the correct answer appears, on average.
So a higher MRR means the search is finding the right stuff much more reliably and putting it near the top.
Precisely. An 86% jump in text-to-code search could fundamentally change how developers find code snippets, potentially saving enormous amounts of time. It's like upgrading from a standard library catalog to a hyper-intelligent librarian who instantly knows exactly the code you need.
Now, the researchers also looked at different ways to create these adapters. They tried a task-wise approach, sort of general for code retrieval,
focusing on the task itself.
and a language-wise approach, making adapters specific to each programming language like Python or Java.
Right. They wanted to see just how much those language-specific details matter for code retrieval. Is it better to be a generalist or a specialist?
Interesting. So in this deep dive, we're going to unpack how this LoRa code technology works, why it gets these results, and why it's such a big step forward, even if you're not deep into computer science yourself. We'll try to use some analogies along the way.
Sounds good. And to really appreciate LoRa code, we need to circle back to those problems with existing code search methods. We touched on it, but traditional semantic search just isn't built for code's precision.
Right. The keywords are strict. Syntax varies wildly.
Exactly. What looks like a tiny change in one language might break everything, or mean something completely different in another. It's like searching highly technical schematics. A tiny symbol difference can change the entire function.
That's a good analogy. Like legal documents, too, where one word can change the whole meaning. A missing semicolon might be fine in Python, but a disaster in C++, say.
Precisely. And standard semantic search often just isn't sensitive enough to those critical differences.
Plus, that context issue again. A few lines of code out of context.
Can be almost meaningless. You need to know the variables, the surrounding logic, the program's goal. Now, existing models, CodeBERT, GraphCodeBERT, Unix Coder, Star Coder, they've definitely pushed things forward.
They have.
But they often have limitations. Sometimes it's the scale they were trained on, which affects how well they generalize. Sometimes it's their architecture, often BERT-like, which, as we said, stands for bidirectional encoder representations from transformers. These architectures might not be perfectly suited for really deep semantic retrieval.
So they're good tools, but maybe not the final answer for all search scenarios.
Kind of steps on the path, but not the destination. And then you have those high-performing proprietary models. They often do incredibly well.
But they're black boxes, essentially.
Largely, yes. We don't always have full insight into how they achieve their results, plus the cost and the fact they might be general LLMs first, code embedders second. Their main goal might not be optimizing specifically for code retrieval above all else.
Right, and adapting those huge models for cross-language search is where the resource bottleneck really hits hard.
It demands serious compute power and time, putting it out of reach for many labs or companies.
Okay, challenge is clear, so let's dive deeper into the LoRa code solution. Parameter-efficient fine-tuning, PEF, using LoRa. What's the core insight behind LoRa?
The core insight is realizing that even in these massive models with billions of parameters, the actual changes you need to make for a specific task like code retrieval might live in a much, much smaller mathematical space, a low-rank subspace.
Okay.
So LoRa cleverly injects pairs of these small, low-rank matrices into key parts of the model, usually the attention layers. And the really crucial bit,
What's that?
the original weights of the big model stay frozen, untouched. You only train the parameters in these small, newly added adapter matrices.
Ah, so you're not messing with the base knowledge the model already has. You're just adding these focused adjustment layers on top.
Precisely, like adding specialized lenses to a powerful telescope. You don't rebuild the telescope, you just add the right filter for the specific thing you want to see clearly.
And you said these adapters are tiny parameter-wise.
Incredibly tiny, between 1.83% and 1.85% of the original parameters in their experiments.
That's wild.
It is, and that massive reduction is why it's so much cheaper and faster. We saw the 25-minute training time on 2 million samples. It gives you that best of both world performance close to the big models, but with the efficiency of much smaller ones.
And it didn't sacrifice performance, it actually boosted it, especially for text-to code.
Correct. Those adapters, fine-tuned with LoRa, led to big jumps in MRR at 1. That means getting the single best result right at the top.
And they specifically looked at making adapters for each language, too.
Yes. For text-to code, they built separate adapters for Ruby, Go, PHP, Python, Java, and JavaScript. And that's where they saw some of the biggest gains, by really specializing.
Makes sense. The paper has that figure 1 diagram showing the whole flow, right? Input meets base model plus LoRa, pooled embeddings, contrastive trainer, similarity scores, MRR.
Exactly. It shows the pipeline clearly. You take the input, code or text code, run it through the LoRa enhanced base model, like CodeBERT or Unix Coder.
Which produces these pooled embeddings, basically, vector summaries of the meaning.
Right. Then the contrastive trainer refines these embeddings. Its job is to pull embeddings of similar things closer together in that vector space and push dissimilar things further apart.
Like organizing a library, so similar books are on the same shelf.
Good analogy. And finally, you calculate similarity scores between the query embedding and candidate code embeddings to rank the results and measure the MRR. It's streamlined for efficiency and accuracy.
Okay, cool. So To really get why LoRa code is an advance, maybe we should quickly recap those base models it builds on. CodeBERT first, you said bimodal.
Yeah, CodeBERT was important because it learned from both code and natural language descriptions simultaneously, using techniques like masked language modeling from NLP.
So it learned connections between words and code tokens.
Right. But its main limitation was treating code just as a flat sequence of tokens. It didn't really grasp the deeper structure, the grammar of the code.
Like knowing the words but not the sentence structure.
Pretty much. That limited its understanding, especially for complex coding or different languages.
Then came GraphCodeBERT. How did that improve things?
GraphCodeBERT added understanding of the code's data flow graph. Think of it like a map showing how data moves through the program, which variables are used where, the sequence of operations.
So it understands the process better, not just the components.
Exactly. It gets more insight into what the code is doing, like seeing the connections in a circuit diagram, not just the list of parts. That helped with tasks like finding bugs.
Makes sense.
Yeah.
And Unix Coder, aiming for unification.
Unix Coder tried to create a single, unified way to represent code across different forms, natural language text, the source code itself, even abstract structured views. It used cross-modal pre-training to link these representations.
So it could handle code translation or code completion well.
Yes, it showed strong results there, kind of like a universal translator for code-related stuff.
And StarCoder, big model, big data.
Very big. Transformer-based, trained on a massive data set, over 80 languages. Known for excellent code generation and completion.
But the downside?
Huge computational cost, both for training and using it. And the training data is proprietary, which limits openness and reproducibility.
Okay.
Yeah.
And briefly, Code T5 and Code T5 Plus other.
They use an encoder-decoder setup, good for transforming input to output, like summarizing code or generating documentation. Code T5 Plus is interesting because it can build on frozen large language models, making it more efficient than training everything from scratch.
Now, that Udpala study from 2023 you mentioned, finding that older models struggle to separate language-specific syntax from general semantics, that seems key.
It really is. It suggests that trying to create one universal representation might force models to compromise. They might get confused by language-specific details when trying to grasp the underlying language-agnostic logic.
And performance even improved when they removed language specifics during testing.
Yes, which seems backward, but it highlights the difficulty. It strongly supports the idea behind LoRa code's language-specific adapters. Sometimes specializing is better than trying to be a jack of all trades.
Okay, so that sets the stage for the models. Now, evaluation, you need good benchmarks. Tell us about Codex GLUE.
Codex GLUE is a big one. It's a benchmark suite covering tons of code intelligence tasks, code search, summarization, translation, defect detection. Crucially, it provides standardized datasets and metrics.
So everyone's playing on the same field, using the same ruler.
Exactly. It allows for fair comparisons between different models and approaches.
And XL cost. The name suggests cross-lingual.
Yes, XL Cost focuses on multilingual code intelligence. It has code in 7 languages where snippets are semantically aligned. They do the same thing, just in different languages.
Perfect for testing if a model understands the core logic across languages.
Precisely. Great for evaluating cross-language code search or translation.
Then COSQE, that was the question answering one.
Right. Natural language questions paired with code snippets that answer them. The key here is that it's human annotated.
Meaning high-quality, reliable connections between the question and the code answer.
Exactly. But its main focus is Python, so it's less useful for broad, multilingual evaluation on its own.
And finally, the CoIR benchmark, code information retrieval.
CoIR is laser-focused on code retrieval tasks, both small and large scale. Evaluations on CoIR have really shown that performance gap between open source models and the big proprietary ones.
Highlighting the need for something like LoRa code.
Exactly. It shows where the state of the art is and where improvements are needed, particularly in open, efficient models.
Okay, benchmarks covered. Let's really dig into the LoRa technique itself. Low-rank decomposition. How does that work again in these LMMs?
Okay, so imagine the attention mechanism in a transformer. It uses matrices, big tables of numbers, to figure out how different parts of the input relate to each other. Fine-tuning usually means changing all the numbers in these big matrices.
Which computationally expensive.
Very, LoRa says. What if the important change needed for this specific task can be represented by multiplying 2 much smaller low-rank matrices?
Smaller matrices, meaning fewer numbers to change.
Exactly. So LoRa inserts pairs of these small, trainable, low-rank matrices alongside the original large attention matrices. The original matrices are kept frozen, their numbers don't change.
Got it. So all the learning for the new task happens only within these new small matrices.
Precisely. You're adjusting far fewer parameters, drastically reducing memory and compute needs, but still effectively guiding the model's attention for the specific task. It's mathematically clever and practically very efficient.
Like adding fine-tuning knobs instead of rebuilding the engine.
Perfect analogy. And you can even have different sets of knobs, different LoRa adapters for different tasks, loading them as needed without disturbing the core engine.
The paper mentioned Gina AI's embeddings as an example using LoRa.
Yes. Gina Embeddings v3 uses LoRa adapters to improve performance for things like multilingual search and handling long documents, all while keeping the embedding generation efficient. It's a good real-world proof point that this approach works well for improving embeddings.
Okay, LoRa gives us the efficiency, but how does the learning actually happen? You mentioned embeddings and contrastive fine-tuning.
Right, good embeddings are the goal. We want code snippets with similar meanings to have similar vector representations points close together in that high-dimensional space.
So search becomes about finding nearby points.
Exactly. Contrastive fine-tuning is a technique to achieve that. It learns by comparing things.
Comparing how?
It takes pairs that should be similar, like a code snippet and its documentation, a positive pair, and trains the model to make their embeddings closer.
Okay, pull the positives together.
And then it takes pairs that should not be similar, say that code snippet and documentation for a completely different function, a negative pair, and trains the model to push their embeddings further apart.
Push the negatives away. Makes sense.
It uses mathematical loss functions, often borrowed from computer vision, like contrastive loss or triplet loss, to quantify closeness and farness and guide the training.
And LoRa plugs into this how?
LoRa makes this contrastive fine-tuning process much more efficient. You're only updating the small LoRa weights to achieve this pushing and pulling of embeddings, not the whole massive model. So you get the benefits of contrastive learning, better semantic organization of embeddings, without the huge cost of full fine-tuning.
It's a lightweight way to specialize the embeddings for similarity.
Exactly. Studies show combining LoRa and contrastive learning is effective for semantic search, retrieval, classification, with low overhead.
What about that LoRa work on contrastive pre-training with data augmentation? How does that fit?
That's about improving the initial quality of the embeddings even before fine-tuning. They'd augment the data, maybe mask parts of the code, rephrase comments, and use contrastive learning to teach the model that the original and augmented versions still mean the same thing. It makes the base embeddings more robust.
Okay, strengthening the foundation. And Neelakantan et al., training separate text and code models.
Their approach used contrastive learning too, but trained separate embedding models for natural language and code using pairs from CodeSearchNet. They showed you could get good results training them independently with a contrastive goal, specifically using in-batch negatives, basically using other examples in the training batch as the dissimilar ones.
Got it. And you mentioned Guillemot et al., briefly mentioned PEF LoRa, but didn't detail it much.
Right. Sometimes papers mention techniques without a deep dive. It just highlights that LoRa code's contribution includes a more thorough implementation and analysis of LoRa specifically for code retrieval.
And comparing LoRa code to CodeXM, again, the key difference.
CodeXM uses powerful, instruction-tuned large language models. It performs very well, even beating Voyage code sometimes.
But model, big resources needed.
Exactly. High cost, high compute. LoRa code takes a different path. Use LoRa on smaller, more efficient base models like Unix Coder. It aims for similar top-tier performance, but with drastically lower resource needs, making it more practical.
Okay, that clarifies the landscape. So let's get into the LoRa code implementation specifics. How did they build it?
They designed it for those two main tasks: text-to-code, find code from description, and code-to-code, find similar code. The pipeline is similar for both.
Input tokenized, LoRa enhanced base model, and very embeddings, similarity, rank.
Pretty much. Input code or text gets broken into tokens. These go into CodeBERT, Graph CodeBERT, or Unix Coder, but with the LoRa adapter layers added in, the model outputs embeddings. Then you calculate cosine similarity between the query embedding and candidate embeddings, rank them, and evaluate with MRR.
And those base models were enhanced with LoRa just by adding those low-rank matrices into the attention layers while keeping the rest frozen.
Correct. Only the parameters within those small LoRa matrices get updated during the fine-tuning specific to the code retrieval task. That's the efficiency secret.
Tell me about the contrastive trainer. What does that do?
It's a custom piece of software they built based on the Hugging Face trainer library. Its specific job is to manage the contrastive learning process.
So it handled the pushing and pulling of embeddings.
Exactly. It calculates the loss based on the cosine similarity between query embeddings and positive-negative code embeddings, and updates the LoRA weights to minimize that loss, effectively teaching the model to create better organized embeddings for retrieval.
And the pooled embeddings, how are they made? Averaging hidden states.
Yeah. So after the model processes the input tokens, it outputs a sequence of vectors, one for each token. These are the hidden states. To get a single vector representing the whole sequence's meaning, they average these hidden state vectors.
It's a simple average.
A simple average, yes. But crucially, they ignore any padding tokens used to make sequences the same length in a batch because those don't add meaning. This average vector is the final pooled embedding for the code or text.
Got it. Tables 1 and 2 had the hyperparameters. Anything stand out?
Table 1 showed pretty standard training settings, batch size 16. Just one epoch of training, which again shows LoRa's speed, a learning rate scheduler. Table 2 had the LoRA specifics. They tried ranks like 16, 32, 64 for the matrices.
Rank meaning how complex those small matrices are.
Sort of, yeah. Higher rank means more parameters in the adapter, potentially more expressive power, but also slightly more computation. They also set LoRA alpha, a scaling factor, targeted the query and value parts of attention, and used dropout. Standard LoRA setup, really.
And they fiddled with StarCoder's layers.
Yes, because its architecture is different. They found targeting query and value in the middle layers seemed best for retrieval with StarCoder, but overall, StarCoder wasn't as strong for retrieval as the others, likely due to its generation focus.
Okay, now the two adapter types. First, the task-specific ones. How did they implement those?
Using that contrastive trainer, they fine-tuned the models specifically for either text-to-code or code-to-code. For code-to-code, the input was pairs of similar code snippets. Embeddings were generated, aiming to capture similarity even across languages implicitly.
And for text-to-code?
The input was pairs of natural language docstrings and their corresponding code snippets. Again, generate embeddings for both. Use the contrastive trainer to pull related text code pairs together. Then for any query, text or code, calculate similarity to candidates, rank, and measure MRR.
Straightforward enough. But the language-specific approach seems more novel here. How did they create adapters tuned just for Python or just for Java?
This was key. They took the multilingual Code SearchNet dataset and split it up by language. So they had a dataset of only Python code docs, only Java code docs, and so on for Ruby, Go, PHP, JavaScript.
Ah, so they created separate training sets.
Exactly. Then they fine-tuned a separate LoRA adapter using only the data for that specific language. One adapter trained just on Python, another just on Java, etc.
So each adapter becomes an expert in understanding the nuances of just one language.
That's the idea. The fine-tuning process, contrastive trainer MRR evaluation, was the same, but the training data was language-specific. This allowed the adapters to specialize deeply.
It makes so much sense. You'd expect a model trained only on Python to get really good at Python-specific quirks, better than a model trying to juggle Python, Java, and Go all at once.
Exactly. It can focus on Python's indentation rules, dynamic typing, common libraries, without being confused by Java's syntax or Go's concurrency patterns. Specialization often leads to deeper expertise.
Okay, so they built task-specific and language-specific adapters. How did the evaluation go? What were they trying to prove?
3 main goals for evaluation. 1, how does LoRA code compare to the base models without LoRA? 2, how much compute cost does LoRA actually save? And 3, crucially, language-specific versus task-specific adapters, which works better and why.
Let's start with text-to-code search. Table 3 look at the XL cost dataset. What did that show initially?
That was interesting. On XL cost, which is multilingual, the initial task-specific LoRA models didn't show a huge jump over the Unix coder base model. Sometimes, especially with higher ranks, performance even dipped slightly.
So LoRA wasn't a magic bullet right away for multilingual text-to-code.
It seemed that way on XL cost. It suggested maybe the task-wise approach struggled to generalize across many languages with LoRa's limited parameters.
But then they used the COSQ dataset, which is just Python Q&A. What happened there?
Big difference. Table 4 shows that when they fine-tuned a combined LoRa adapter on COSQ, Python only, the MRR jumped by 14.8% and NDCG at 10 by 13.5% compared to base Unix coder on the same task.
A significant improvement. Why the difference between XL cost and COSQ?
They figured a couple of things. COS-QA is human annotated, meaning really strong query code relevance, but crucially, it's only Python. Training the task-specific adapter on the multilingual code search net might have diluted its ability to learn Python specifics, whereas training on COS-Q let it focus.
Reinforcing that language context matters a lot for text-to code, which leads us to the language-specific adapters. Table 5, these were the game changers, right?
Absolutely game-changing. Table 5 shows massive improvements when using language-specific LoRA adapters on Uniscoder for text-to-code.
Yeah.
Across Ruby, Go, PHP, Python, Java, JavaScript, big gains in MRR and NDCG.
And that Python number again?
Up to 86.69% increase in MRR for Python. But substantial gains everywhere. PHP over 60%, Go over 40%. It clearly shows specializing the adapter per language is highly effective.
Wow. And did the amount of training data per language make a difference?
Yes, a clear trend. Languages with more data in Code SearchNet, like Python and Go, saw the biggest improvements. Languages with less data, like Ruby and JavaScript, still improved, but by smaller margins. More data helps the specialized adapter learn better.
Interesting. And the baselines were similar to previous work, but the LoRA improvement was much bigger.
Correct. It suggests LoRA is particularly good at extracting that extra performance for language-specific retrieval from these base models. They gave examples, too, like how the Python adapter might better grasp indentation significance, while the Go adapter gets Go's stricter typing.
They did mention a limitation. Code SearchNet and COS-QA are mostly code comment pairs or text queries. So they also tested code-to-code search using XLCost. How did that go? Table 6.
That went really well, too. For code-to-code search on XLCost, the LoRA adapters consistently outperform the base models, graph codebert, across all 7 languages in XLCost.
Even against Unicoder, the best base model.
Yes, even a LoRA adapter with a fairly low rank 32, substantially boosted MRR over Unix Coder for code-to-code search.
And again, this was achieved using only that tiny fraction, 1.8% of trainable parameters.
Exactly the same efficiency. Strong performance gains for both text-to-code with language adapters and code-to-code with task adapters here, using very few trainable parameters.
Did LoRA add much delay? Table 7 looked at embedding generation time.
According to Table 7 in the appendix, the time taken to generate embeddings with the LoRA models was generally comparable to the base models, so the performance didn't seem to come with a significant latency penalty.
And Figure 2 visually confirms the trends, showing LoRA consistently improving things, especially with more data.
Yes, that figure nicely summarizes the consistent positive impact of LoRA, particularly for text-to-code with language-specific adapters.
Okay, let's wrap this up. What are the absolute key takeaways from this LoRA code research?
The main takeaway is that LoRA code, using LoRA for parameter-efficient fine-tuning, is a really effective and efficient way to boost code embedding quality. It gives significant accuracy improvements for both text-to-code and code-to-code search.
And it does this with drastically reduced computational cost compared to full fine-tuning.
Precisely. Low overhead, big gains in metrics like MRR and NDCG across multiple languages.
And that finding about language-specific adapters being superior, especially for text-to-code, seems critical.
Absolutely. Tailoring the adapters to the specific syntax and semantics of each language allows them to capture nuances much better than a single general-purpose adapter trying to handle multiple languages. That was a very strong finding.
And they plan to explore this language-specific idea further for code-to-code search, too.
Yes, that's mentioned as future work, seeing if specialized adapters also significantly benefit finding similar code within the same language and comparing adaptation across languages.
This has been fascinating. Seeing how a technique like LoRA brings such efficiency and performance boost to something as complex as understanding code across languages, it really opens up possibilities. Which leads to a final thought for our listeners. Considering LoRA code's success, where else might these parameter-efficient adaptation techniques be really powerful? Think about other areas dealing with diverse, context-heavy data, maybe scientific literature, legal text, complex logs. Where could targeted efficient adaptation unlock similar breakthroughs? Something to ponder.